Hi there. Just to wrap up this question then, notice this probability is, I think, shockingly small. So look at what's happened. I'm trying to determine the probability that the antibodies are actually present in the blood given that a positive test result has been received. Well, that likelihood is less than 63% of the time. It's 0.627. So it is plausible that even though I've seen a positive test, that the antibodies may not actually be present in the blood. So the issue is, this is why you need to retest before you make a decision regarding treatment when it comes to some type of, especially life-threatening medical procedure where the situation can get serious. When you see a positive test result, that doesn't necessarily imply that the disease state is in fact a disease state that you have. This is where you need to go back and retest or use a different test, or you need to reevaluate the circumstances. So again, I'm surprised how low that probability can be. So something to think about though, this question depends on one important assumption. So look, from the very beginning, we assumed that 1% of the population was carrying the HIV antibodies in their blood. So, of course, different segments of the population, there may be a different percentage within that segment of the population, a different percentage that actually carries HIV antibodies in their blood. So something to think about, I want you to do a similar analysis. So actually, I've given you the same diagram. In fact, you can use exactly these four probabilities again. So these four probabilities still apply from the front side. Those four probabilities you'll have to use in organizing your tree. But the difference is we're going to look at a higher risk group. So in this second question, we're going to do a very, very similar calculation. But we're going to look at the clients, for instance, of a drug rehab clinic. So being a user of drugs, especially intravenous drugs, because of the sharing of needles, this is one way in which blood is transmitted from person to person. This is one way in which HIV can be transmitted from person to person. So a drug rehab clinic would be considered a higher risk group. And so what we need to change then is, let's presume, for instance, that 10% of this population actually carries the HIV antibodies. No, because of that change, it is going to change the first portion of your tree diagram. That's going to change the percentages that you put into this portion of the tree diagram. So understand, our assumption from the front side affected the 0.01 and the 0.99, having the antibodies or not having the antibodies. So now, based on our new assumption of 10%, these values will change in the tree diagram. These will not. So you can use the same ones from the front side of the tree diagram in order to calculate all of these four different events. Once again, you want to add up two of those events to get the probability of a positive test, and then you're going to use the probability of the positive test over here to calculate the probability that antibodies are present under the condition that you've seen a positive test result. And then bottom line, I'm going to ask you to read a little bit and write, just fill in the blank once and write just a very little bit down here at the bottom. Of course, one last thing I want to summarize, and then I'll be done. This calculation for the conditional probability up here, this is a handy calculation to recognize. And just once here, I want to summarize it. I want to write it out in general. This says the probability of antibodies, given the fact we've seen a positive test, this is calculated by looking at the intersection of both of these. So both the antibodies and the positive test, they both have to be there, but we're dividing by the condition. Under the condition that the positive test has already occurred, so we are dividing by the probability of what has already occurred. We're dividing by the probability of that positive test. This is in general the way to calculate a conditional probability. It is just a rearrangement of the formula for multiplying in general. So I just wanted to write that out one time. So recognize then here the probability of an event A, given that B has happened. The way to do this conditional calculation, you can simply look at the probability that both have happened, A and B. So both have to have happened, but we have to divide by the fact that the condition was B, so B has already happened. So in general, that is the way that you can calculate a conditional probability if you don't have a picture and instead you have you don't have a diagram. Instead, you just have the actual numbers, the percentages, the decimals, the fractions. So that's an awfully handy formula. And again, notice if you multiply that, I'll bring it down here and multiply it back out. All this is a rearrangement of the general formula for multiplying. So if I cross multiply here, this is the probability of B times the probability of A given B. And cross multiplying, that's just equal to the probability of A intersect B. So notice this is just the general multiplication formula. The probability that A and B has happened, you can start with the probability of B and then multiply to the probability of A, but given that you already know B has occurred. So by taking this and dividing both sides by B, we can work backwards, if you will, and we can get to this formula for calculating conditional probabilities. It can be handy. That's just a rearrangement of the general multiplication formula. That's what we're using in this calculation up here. And that's probably something that you would want to know going forward. So your job is to finish this question. This is something that I will be collecting the next time I see you. Hope this has been helpful. And at some level, I hope that this has been interesting too, because this is an actual, very practical application of probability to a real life circumstance that I think everybody should be aware of. Bye-bye.